Sure this is working. Yeah. So today, the two examples that we'll go over, one's related to the thermal actuator that we just done, but it's the other example I was telling you about where what we would like to do is for the V-shaped thermal actuator, we would like to go through a sweep in order to determine the optimal angle. Okay, and there's one optimal angle, and we'll figure out how to do that. And so the geometry that we'll put in is something that's going to look like this. So here's our anchor. We have a beam here that goes off at some angle. It meets up with another beam right here. And this is a bad angle, okay? But it's just giving you guys an idea of what it's going to look like. And it's going to be, let's say, a beam that is like this. And here's the angle that we want to optimize. Okay, this is ground right here. We're going to apply a voltage through here. Have the current go through. The current is going to heat this up. There's going to be some thermal expansion on the beams. And this point right here is going to deflect upwards because of that. So the question that we're going to answer today is, where should this angle be in order that the deflection that this experiences is the greatest for whatever voltage we put in? Okay? So we'll answer that. The other thing that we'll do is something that involves three different multidisciplinary, three types of disciplines. I mean, three kinds of physics domains. So we've done two before. Now we'll try to do three. And this has to do with chemical etching, flow rate, mass diffusion rate, and moving boundaries, meshes. And so it's kind of complicated. And that's the file I just sent you guys for entering the parameters. So basically, and we talked about this a little bit before, how things are made at the microscale where you have a substrate, typically a silicon. Okay, and then what you do is you deposit through all kinds of ways. It could be chemical vapor deposition, or what have you, or you could spin on some sol gel, or just various ways. There are various ways to put on different layers at a time. Okay, and then, so let's say you put on the layer, and what you want to do is, let's say that layer is, I don't know, some type of, let's say this is silicon dioxide. So there are certain chemicals that will etch one type of material much faster, much faster than the other type of material. And that's the kind of thing you want. So let's say this is silicon dioxide, and what you want to do is put on maybe some photoresist over that. And then let's say you have a mask, and then you want to shine some light through that mask in order to break some of the bonds. So light's coming down, and then the light is shining in this area right here. Okay? These are the bonds that are affected. And so what happens is that now you have this material, and there's certain type of etchants that will etch away photoresist where the bonds are broken and leave behind photoresist where the bonds are not broken. And so this part goes away. And so what is exposed now is this surface, this silicon dioxide layer. So I'll just put PR for photoresist and put SiO2 for silicon dioxide. So the silicon dioxide is exposed. And so what you can do is, it doesn't have to be silicon dioxide. It could be other things like, let's say it's something like, okay, you can say it's nitride or it's just a different kind of material. Okay, so then what you do is you can etch directly through this, and it could be a physical type of etch that sort of like leaves a hole through that. Then you can get rid of your photoresist. There's a chemical that just gets rid of photoresist and leaves alone these other types of materials, right? And now this area is exposed. And now you want some type of chemical etchant to come in here to just etch away this material and leave behind this other material. Okay, so you're flowing through some chemical and it's going to start etching away. Well, what happens is that first it looks like this, then it starts, looking like this, and then it starts looking like this, and it takes on this weird shape, right? Where this direction is etching a whole lot faster than, say, that direction. And the reason is because the mass diffusion rate over here is more open, so some etchant could get through here, attack the surface, your latest surface, and then carry that species out, versus over here where your concentration is a little lower, and so the etch rate on the sides are going a whole lot slower than etch rates going down that direction. Okay, and that's what we're going to model today too. And we'll see how the wall begins to, the surface begins to start moving away from the surface. And it leaves behind this material right here. All right, so let's first do this one right here. Now that geometry is a little easier to do. Oh wait, let's talk about how we're going to do this geometry. So let's say the length of that's going to be L. Okay, so what we'll do is, let's say this is our point 0, 0. And then we'll put this in there, and we'll parameterize it by theta, and then we'll also sweep theta too. And then what we'll do is, for this point up there, we're going to go over, we have to position that point right there, so it's going to go over some L cosine theta, and then go up some L sine theta. That's going to be our point right there. It's going to be the same beam, but instead of having it go up that angle, we're going to have it go down that angle to meet back over here. We'll put in some bond pads, and we'll stick that on there too. Okay, so let's start COMSOL. Okay, so for this first one right here, it's going to be 2D. No, wait, we can make it 3D. Yeah, let's make it 3D. And we'll go to structural mechanics. We'll go to thermal stress and do this Joule heating thermal expansion. And we'll add that. Okay, then we'll go to study. And then we'll do stationary. And then we're done. Okay, so now let's change our length scale to microns. Right here, micrometers. And let's go to our geometry. Let's put in a work plane. And then for our plane geometry, let's add in a rectangle. And that's going to be that first rectangle. Got my pointer. It's going to be this first one right here. And so let's put in L. Oh yeah, we got to define L. So we'll do that in a second. And for the height, let's put in let's put W1 and L1 for the length and the width. So let's go back here and define the length and width. So let's say L1, the length, that's going to be, I don't know, let's say 100 microns. So 100 in micrometers in brackets. For W1, let's say that's going to be 2 microns. So 2 bracket UM. Okay. So now the L1 and W1, they're no longer red. So we can do build all and see what it looks like, and then do zoom extents to see what that beam looks like. Okay. Now we're going to rotate it up by theta. So let's type in theta for the rotation angle. Okay. And of course theta is red because we haven't defined it yet. So let's go to parameters and let's put in theta. Now theta is kind of weird, right? Because, do you want to do it in degrees or radians? So it's kind of weird. So let's put in like let's make it degrees, and we'll put degree in the square brackets, and then COMSOL will know how to deal with that. So we'll start off with, I don't know, 5 degrees. Okay, and we'll put DEG for degrees. Now if you look what happens here, if you look at the value, it put it in radians. Okay, and that's just because it knows how to handle degrees. Say, well, if it's 5 degrees in radians, which it deals with, is this right here. So let's go back to our rectangle, and then we'll put in theta. And as you see here, it is in degrees already. So do build all, and it should angle up at 5 degrees, like that. Which makes sense. Okay. So let's put in another rectangle. So go to plane geometry, go to rectangle, and for the width, put in L1 for the length, and for height, put in W1. So now we're going to put that other rectangle right here. That's what this second beam is over there. And so what we'll do for X, we have to put it right here at the tip, right there. So that corner right here at 0, 0, as you can see, at 0, 0. So we'll say that's going to be over, in the X direction, L1 times cosine, and we'll put theta in here. But we have to tell it that our theta is in terms of degrees, and it'll know how to handle it, hopefully. And then for Y, we'll go L1 times sine theta in degrees, bracket in parentheses. Okay? And then do build all. Oh, wait a minute. We forgot the angle. So that's why it's going off straight. So put negative theta for that. So it should look something like that. Okay? Actually, for our case, let's change theta to make it more pronounced, just because let's put like 20 degrees instead. Yeah, just to make it more pronounced for our own benefit. So it should look something like that now when you build all. Okay? So now let's add in the anchors in that middle backbone piece right here. Now, the reason for that backbone piece is typically when you have something like that, they usually have a lot of them. And all of these right here are sort of like attached to something. Like that. And so this is like one component. So you can just add another one to that, and then this beam, this backbone right here will attach to another one as you go down to make something like that. So that's what that is for. Okay, so let's go to plane geometry, right click on it, add another rectangle. And so we'll try to make this rectangle right here, which is a bond pad. So let's make the width, I don't know, how about 10 times W1? And same with the height, 10 times W1. Let's see what that looks like. So let's do build all to see what it looks like. That's fine. Now, it's kind of like off, right? It's So what we'll do is this. Let's rotate it 180 degrees first off. And then let's change the corner. Let's make it go in a Y direction. Let's make it go up 5 times W1. Yeah, something like that. So you see what we did? It was sitting over here, we rotated it around, and then we made it go up. So if you like zoom in to this point right here, you'll see that it totally intersects that. And we'll do a unionize to put it all together. So that's fine. And then let's do another one. So go to plane geometry, make another rectangle, and we'll do the same thing to the other side. We'll go 10 times W1, 10 times W1, and for the X, we have to move that over, let's see, 2 times L1 times cosine, and then theta degrees. I think that might do it. Let's see what that looks like. Yeah, see? And so we had to go to L1 cosine, right, to get over there. And then we don't need to rotate it, but we do need to shift it down a little bit. So let's say negative 5 times W1 to shift it down. See what it looks like. Yeah, there we go. So should be like that. Look at sort of symmetric. And I just thought of this. What we could have done, since this is a symmetric structure, we could have just built half of it and then flipped it and mirrored it to the other side. And I guess if we were going to do this again, that's what I would do. But okay, so we've gotten this far. So let's put in that backbone piece right here at the very top. So let's say rectangle, and let's make that one. How about 4 times W1? Might be a good size. And then let's make it, how about 10 times W1 for the size. And the coordinate of that is going to go over there, and how do we want to do this? It's going to go over and up, but then we have to adjust it slightly once it gets over there. So let's just make it go over and up. So that'll be L1 times cosine theta in degrees. And then for the y, L1 times sine theta, and that's in degrees. And let's see what that looks like. Yeah, so it's almost where we want it, but we want to move it over to the left a little bit, and then we want to move it down too. So halfway for both of those. So for the x, we're going to say minus, since the width is like 4 W1, let's say minus 2 W1. Let's see where that gets us. Yeah, that's fine. And then for the y, instead of it being 10 W1, let's put 5 W1. Yeah, there we go. Okay. Huh? Oh, you don't? Let's try it out. Have you guys tried that? Yeah. And it works? Cool. Okay. That's great. Now let's see. Okay, so let's do a unionize. Let's union everything together, and then we'll extrude it to 3D. Okay, so go to plane geometry, right-click, go to Boolean, and then union, and then click here. We'll go Control-A, select all. It puts every rectangle in here. We will uncheck keep interior boundaries, and then we'll do build all. And so that's what the structure looks like. Now, when we do a sweep, it's going to go through that whole process and unionize it every time it updates theta. Okay. Now let's extrude to 3D. So go to geometry, right click, and then go down to extrude. And then let's go out like 2 microns. 2 microns. And build all. And there we go. We've got our structure. So, like I said, it's a thermal actuator. Some people call it a heatuator. But some people call this a chevron actuator because it looks like the chevron symbol. Now, okay, so that's the geometry. Now let's go and let's add a material property to this. So let's go to MEMS. Let's go down to semiconductors. I have to move this over so I can see it. And let's go to polysilicon and then add that. Okay, so when we add polysilicon, it has like a little stop here and it's asking us for the electrical conductivity. And of course, that depends on how much you dope polysilicon. So let's put in, I think the number was 5E4 for that. That's all you need to do there, 5E4. Now let's go to solid mechanics. We have to tell it where the anchors are. Otherwise, it has no idea that these things on the side are anchors. So let's go in solid mechanics, right-click on it, and go to fixed constraint. And what we'll do is we'll click on this boundary right here. So try to highlight on it. If you have difficulty highlighting that, you can zoom in. So click on it once, and it'll add. That's boundary 1, and it added it. And then go to the other side and anchor that side too. Try to click on it. I might have to zoom in on this side. So click on, still not. Oh, there it goes. And that's, in my case, is boundary 4. Oh, wait a minute. Is that boundary 4? Well, I'm not sure if that's right. Oh, is it? Yeah, for mine is boundary 22. And also, you'll see the color change as well. That's how you know you got those boundaries right. Yeah, so boundary 1 and 22 for mine. Okay, so that's all we need to do for solid mechanics. For heat transfer, let's go in here and add heat flux. And for this, if you recall, we want it to be convective kind of heat. And the H, if we recall, that was 0.04. And the units are already over here. See that? Watts over meter squared times Kelvin. So we don't have to put the units there, but it was per, I believe, 100 microns. Oh wait, I think we're supposed to go all boundaries. Yeah, select all boundaries and then undo this. Why is this complaining at me? I'm not sure why this is not a black color. Why is it like a, huh? Okay, that's fine. I think it's just like a little warning. I don't know, but I think, okay, so remember how it was done last time where this sort of like dimension right here was, you know, like what size, and before how we did it was the surfaces that were close to the substrate, we made that 2 divided by 2 microns, and the top surface, since that was more exposed to the more ambient atmosphere, we made that 100 microns. And so here we're being a little lazy and just saying it's 100 microns everywhere, which should be fine. So let's go to temperature next. So click on heat transfer, right click on it, and tell it where the temperature is. So the boundary that we're going to select is the substrate boundary. So let's say right here where the anchor is, let's say that temperature has to be 293, right? Because that's connected to the substrate. And let's say this temperature right here, if I can click on, I'm having difficulty with that side. So I'm going to click on this side right here. That's 22. So 22 also has to be a constant temperature of 293 because it's connected to like this reservoir, which is a substrate. And that's, again, that's an estimate because, as you know, the heat generator is actually going to heat up the substrate a little bit, right? So it's not going to really remain at that temperature, but it's a good enough estimate for what we're trying to do. Okay, so that's heat. Now let's go to electric current. We have to tell it where the ground and potential are, right? So let's click on ground, and then go to one side. It doesn't matter which side. Current could go from right to left or left to right. But let's put in ground on this side. Okay, so that side's going to be ground, where it's attached to the substrate. Let's go back to current and tell it where the potential is. And that's going to be, of course, on the other boundary. So over here, and that's going to be the high potential. And let's make that like 2 volts. Okay. And I think that's really it. I think we can go now to this right here and do compute. And I think it should mesh it automatically for us. Yeah, see, there we go. Now, a lot of times before, we'll go to mesh and we'll put, we'll do like a free tetrahedral and we'll tell it fine or finer or regular. But this is just a really quick type of thing here. And we're not really trying to optimize it. But that's what it looks like. And let me go back to the results. So let's go back to stress. It's showing us deflection and also some stress levels. So let's go to deflection. So let's go into here. Let's go to surface. And then I believe what we do, we're going to replace the expression, right? Instead of saying the stress, we're going to tell it to plot displacement. So let's go to solid mechanics. Let's go to displacement, and then let's double click on total displacement, and then plot that. Then that changes what's plotted on the surface to plot displacement. So where we see the orange or the red, that's the displacement right here. And where we see the blue, that's no displacement. Now, one thing I want to mention to you guys is this. Let's go to deformation. Okay? See the scale factor right here? It automatically tries to adjust the scale factor in order to show you what's happening. Because if the deflection is so small that it's beyond the resolution of what is visual, it's not going to, it'll show a color, but it won't really show deflection. So it's trying to show you, well, it goes in this direction, but as you can see, it multiplied it by 26. So if you want an actual deflection, if you want to see an actual deflection, you click on scale factor, and then you change this to 1. Okay? And then you plot it. That's the real deflection. Okay? And of course, as you can see, it's not, it doesn't seem like very much. If you zoom in, you'll be able to see the difference. You see, the outline is where it used to be, and the color is where it is. And of course, if you look at the legend over here, it's in units of microns. So the highest deflection right here, the orange, is 0.35 microns, or 350 nanometers. Okay? So that's how you get the actual deflection. You have to go click on deformation and then change that scale factor. Sometimes, it'll scale it down. Sometimes it'll scale it up, just to, show you what's happening. Okay. So now let's do a sweep. So what we'll do is we'll go to study, and then we'll click on parametric sweep. Okay. Then we'll add one. So we're going to add some parameter to sweep over. In this case, we will open up this box here and click on theta. So we have 3 parameters that we input, and the parameter we're going to choose is theta. And then for theta, let's click on here and choose a range. So here's the range dialog box. So if you click on that, you can choose your range. And let's start at 0 degrees. Now remember, this is all degrees because it's theta. And let's stop at let's stop at 3 degrees, because it's going to be small. And so we're going to sweep between 0 degrees and 3 degrees, and hopefully we'll see a peak somewhere between there. So it's a good guess. And let's say we're going to do a step by 0.1 degrees for each one. And then we'll just replace it right here. So see, it starts at 0, goes by step at 0.1 degrees, and then 3. Now, 0.1, so we're really talking like 30 steps. So it's kind of fine, which could mean that we're going to have a longer solution than maybe we would like. But so maybe initially you want to start off with larger chunks, like maybe 0.5, and then reduce it if you like it to the range you want. So then compute that. Okay, so it's going through that analysis, and here's the measurement bar showing our time. So it looks like that's going to be maybe like 30 seconds or so. Yes.
This the angle.
Oops.
The delta angle above the angle you already drawn.
What was that?
Is this the delta angle above the angle that is?
Oh no, it's going to start. Theta is going to be 0. Yeah, exactly. It's complaining here. That could be. Yeah, that's kind of interesting. I wonder if that's due to my mesh. Maybe it could have been a finer mesh. It didn't surpass my relative error. So, well, it said 0.7. So at least we know it's going to. Okay, so let's go back up to our sweep, and then let's put 0.6. We know converge to 0.6. Right? So let's try that. I think sometimes you run into these convergence problems, and it could sometimes. Oh, come on. Huh?
I think for the sweep, you have to put degrees or change that for right.
Yeah, if you just put.
Oh, yeah, it is in radians. Look at that. Yeah. Thanks for pointing that out. That's very important. Well, that's, I put degrees everywhere. Yeah, I didn't even look at the, we'll put like 2 here. Yes, being very observant. Still an error. Does anyone else have that error? Huh? Okay. Did anyone else have like a sweep that worked? No. It's not good. Let let me try a larger step size. So how about how about 0.5? Let's see what happens. Let me try to do a better mesh. Let's go down to mesh. Where's mesh at? Right here. Let's do our, go down here. Step size is normal. Let's do a fine, maybe, and build all that. Let's do a finer. Maybe that's a little better. Yeah, let's try that one right there. So let's go to primary sweep. I don't understand this. It worked before when I tried it. Oh wait, let me see something. Did I save this? Okay, so this is, yeah, this is what I've done before. Okay, so trying to figure out what I did differently this time. I had that surface. Yeah, this is going by 0.1 too. Yeah. I went into study. If you look at my parameter suite, there's no unit here, and that was my suite. I went from 0 to 4 degrees. Huh? Oh yeah, yeah. And I think the reason why I got away with it last time maybe is in like my geometry. If you look at my geometry, my yeah. I wonder if it's because I have degrees here, and then so it forced it into degrees every time. Yeah, that's the only difference I can see, because even in my mesh, I didn't do anything special with my mesh. Okay, but okay, so like if we go to our derived values, here's a point we're interested in. I'll send this file to you guys, okay? And so, because here's a real thing that we're trying to deal with. Here's this point we're interested in. That's point 28, okay? Then I did evaluate, and then here's the table right here. So when you plot this table, right here, it looks like this. So that's 0.28, and as you can see, it gets really high. And remember, this is theta right here, going from 0 to 4 degrees. Okay? And this is the total displacement in microns, as you see right here. And here's the top. So at this angle, which is like 0.3 or 0.25 or 0.2 something, that is the angle that gives you the best deflection. But think about that. That's 1.2 degrees. If you're a little less than 1.2 degrees, you're down here. If you're a little over, you're over here. So, but for the optimal angle for a structure like that, that's way off my picture. But it's like 1.2 degrees, which is kind of, that's totally not intuitive, right?
Is that material dependent? I mean, if you had a stiffer material or one with a different expansion coefficient, would it be different?
That's a good question. I would say it's not dependent on the material. I think it's more dependent on the geometry. But I haven't checked that out. But of course, it's easy to do here. We know we can just go in there and change our material very quickly to see. But my guess, the peak is independent of your material. However, how high that peak is will, of course, be affected by that. That's my initial guess. Okay, so so I'm wondering how far we can get in the next 20 minutes for our next example. Okay, well, let's start our next example, and let's see how far we get. Okay, so let's go to in here, go to new. And again, I'm going to send you guys the MPH file I just showed you, just so you can run through again, see what that is. And again, I think the only error, the only thing that was different was that I put degrees everywhere, and I think maybe that could be the issue. I don't know. Otherwise, I can't tell what I did differently. So let's go to model. Let's click on 2 dimensions this time. So remember, this time we're going to do this type of etchant type of behavior. So actually, let me show you like what's going on, because otherwise it might be a little confusing. Not to say this will make things more clear, but at least you'll know what's going on. Okay, so we have the picture right here. So there's going to be several equations that we're going to deal with. So one is the mass flux. And this equation is partial C, partial T, plus U, then delta C, plus, that's dotted into D delta C. Okay, so this D right here is a diffusion coefficient. This right here, C, that is the concentration. So that's there. This right here is the flow rate. The velocity of the field. So this is the mass flux for the etching, the etchant. And this is the reason why over here it etches a lot slower than maybe over here. There's another equation we have to deal with, and this is for the etching surface. And it has this particular constraint right here. And that's just the normal vector equals negative Kc. K right there, that is the etching rate. And that's the rate that the surfaces are being eaten away as you're etching. There's also the flow field. This is from the laminar flow. And that equation, which you guys have seen before, because we've used it before, is U. Rho is the fluid density. That's fluid velocity, just like here. We have the pressure. That's rho, that's pressure. This is the identity matrix. You know, it's like this a matrix where the diagonal just ones. This right here, mu, that is the dynamic viscosity. That continues on this line down below. And F is the volume force vector. Okay, and then also this wall right here moves. Okay, and that's going to be our moving boundary. And so there's also a constraint on that. And so this right here, so there is a velocity of that moving boundary, and that equals to d, which is the same d above. M right here is the molar mass, and this right here is the density. Okay. And last equation, there's like a no-slip type of condition that we'll enter in, and that's just this right here, rho. Okay, so basically these are all the mathematical equations that this whole thing is modeling, okay, partial differential equations. And so now the reason that we just click on all these modules is because these things are built in, right? And so someone has already went through the trouble, someone who's a specialist in this field, they already went through the trouble of keying all these things in, and all we're telling it is, what are the parameters? Like we'll put in the concentration, you know, we'll put in just various different things, the etching rate. We'll decide that because the equations, the form of the equations don't change, but maybe the parameters do. And that's the point of having these great modules that we're dealing with. Okay, so the first step, so let's click on the first type of physics. Click on chemical species, which is right here, and then click on transport of diluted species. Click on that, and then add it. So that's one of them. The next thing, over here for concentration, instead of letting it be C, let's call it this, capital CU, and then Cl2. Okay, that's the concentration of the chemical species we're going to be dealing with. So we're just naming it right there. Okay. The next thing you want to do is click on deform mesh, and that's in mathematics. So go to mathematics, and then click deform mesh right here, and is there? Oh, here it goes, deform geometry. Yeah, so go to mathematics, deform mesh, and then deform geometry. And then add that. Now that's the second thing. Now go to fluid flow, which is right here. Click on fluid flow. Click on single phase. Go into there. And then click laminar flow. And then add that. Okay, so we have 3 things going on here. And then let's go to study next. Let's click on stationary and then done. And I don't want to save the changes. Okay. Now, so let's first get those parameters that I emailed you. So go to parameters. This opens up, and then click on this folder right here, load from file. And I put it on my desktop. And it's right here. So go ahead and get that file and put it on your desktop or wherever, and then load that. And then once you do that, all these parameters load up. And so great, we don't have to type in these things. And that was supposed to save us time today. And it saved us a little, but I don't think it's enough. Okay. How's everyone doing? Are we all here? Okay, cool. Okay, so for the next thing, let's go to definitions, which is right here. And then we'll go to variables. We'll click on variables. And then add in, there are 2 variables we have to add in. And maybe I should have did those from file too, but because they're kind of long. But this variable right here, hope you can see it. So it's, if you can't see it, I'll write it out. So R underscore surface.
Is that a negative in the front there? I can't
Yes.
see.
Yeah, thank you. It's negative R underscore surface times capital M underscore capital C and then lowercase u. Then divided by rho underscore capital C lowercase u. Oh, wait a minute. Wait. That's the expression. So copy that and put it into expression. The name is V underscore surface. So V underscore surface. Yeah, so that's the velocity right here. See this moving boundary? That's what that is, of that surface. That's how it's defined right there. And that's why you see like this right here, this MCU is that capital M right there, and rho is the density on the denominator. Okay. Okay, so for the next one, put in R surface, R underscore surface, and then type in negative KF times, and remember that that concentration we put in is lowercase c, then capital C underscore, lowercase u, then capital CL2. So that's the concentration. And I believe that's this right here, that expression right there, the etching rate and the concentration. We just labeled it slightly differently. Okay. And so if you click down, everything should be black, like no warnings, no complaints. Does anyone need me to write this out on the board? Any of those things? You guys good? Okay. Okay, so next let's go to geometry. And then it's all 2D already, so we're not going to have any 3D, which is great. So you can just click straight on geometry and then click rectangle. It'll take you there. And then for the width, put in D_mask. That's a parameter that we added in there. That's why it knows what it is. And then put H_mask. And then build all. So that's the first part. Then go click a second rectangle, get another one. And then for that one, put in, for width, put in H_boundary_layer. So it's like that. So H_boundary_layer. And that's a parameter that we defined. And then for height, put H_seed_cavity. That's also something that we defined. Okay? Now for the position, put in -H_seed_cavity. And for the Y, same thing. So you can just like copy and paste. So -H_seed_cavity and build all. And so it should look like this. Okay, and this part right here, what this is going to be is actually like this right here. This piece coming in right here is going to be like this. And this piece under here is going to be like what's being etched out. But we're like, just getting it started. Okay, so now let's put some fillets in there. So, if you go back to parameters, you can see where it says H_mask and D_mask and H_seed. We defined all those things. The density, the rate, all those things were defined. Okay. Well, now let's go to fillet. That's down here. And then so for the fillet that we want this one right here and this one. Those two at the bottom. And for the radius of curvature, we want H_seed_cavity divided by 2. So H_seed_cavity divided by 2. And then build all. So it should look like that. And so what that means is that we are building this right here. Starting off just looking like this. Okay? That's what we're building. This piece right here. Now let's put in a big rectangle for the flow coming through. And so let's go to a third rectangle. So geometry, rectangle, and for width, put in D_mask times 2. For the height, put in 3 times H_mask. Times. Okay. And for the X position, put in -D_mask divided by 2. for the Y position, just put in H_mask. And then build. So it should look like this. So for this right here, we have our chemical species is coming in this way and flowing right across. Some of it is going to come down here and interact with this surface and start etching it away. This part right here is not going to get etched away because this chemical species only reacts with this kind of surface, and this right here is like the mask over that surface to protect it. But it's going to etch all under here, down here faster, and under here too. Okay, that's all the geometry. Now let's see, we have one more minute left. So it looks like we're gonna have to save this before we continue. Yeah, so I guess we'll save it right here and then we'll continue the rest on Thursday. And yeah, so go ahead and save it. And we'll come back on Thursday and finish it off.